In the naive algorithm to solve the sub-array sum problem, we are doing k minus 1 summations n minus k plus 1 times. N here is the length of the list, k is the length of the window. Now these numbers could get a little bit confusing, so let's make it a bit more concrete. Let's say n is 100, which means I have 100 items on the list, and say k is 3, so the sub-array size is 3, so the window of 3. Basically, for every sub-array, we are doing k minus 1, which is 2 summations, and totally there are n minus k plus 1, 98 subarrays. So total number of submissions that we are doing is 98 times 2, which is in formula wise, it's k minus 1 times n minus k plus 1. In fact, this was evident from the way we wrote the code. Remember, the outer loop tracks the start of the subarray. It's also telling me how many subarrays there are. There are totally n minus 1, n minus k plus 1 subarrays. We spoke about this. And within each subarray, there are k values. So we are doing k minus 1 summations to get this, to get the sum. Again, pictorially, basically for a k of 3, we are doing 1 and 2 summations, 1, 2, and so on and so forth. And there are, let's say, n minus k plus 1, or for example, in case of n being 100, 98 such subarrays. So very, logical, but do think about it. Now, what does this mean with respect to the complexity, the big O notation? Well, think about it. K is always going to be smaller than n. In fact, in most cases, we can imagine that k is much, much, much smaller than n. So, for example, when we are doing, let's say, over a data of 1,000 items, we might do a window of, say, 15, 20, maybe something like that. So, k is always going to be much smaller than, n, and we can hence represent k as c times n, where c is not just less than 1, but in fact, much lesser than 1. Now I can substitute Cn into this formula over here, which is here, Cn minus 1 times n minus Cn plus 1. Now again, the exact value of this doesn't really matter. It's the scaling that we are interested in. And usually we look at the most dominant term, as we have seen in the big O notation. The most dominant term here is going to be C times n square. Now once again, in terms of the big O notation, C doesn't play a role. The order of this algorithm hence is order of n square. Now this is where this is the most interesting point, that look, this algorithm's complexity is scaling as n square, which means that if I make the, let's say, the array, let's say 2 times as large, the list becomes 2 times as large, then I'm going to do approximately 4 times as many, let's say, computations, and that's going to be 4 times the runtime. So square complexity we have seen is quite builds up quite fast. We saw that, for example, in the pair sum problem. So this is similar, order of n square. Question is, can we do better? Yes, indeed, the answer is yes. The way to think about it also is that, look, are we doing more work than what is actually needed? In fact, in this case, the answer is yes. The naive algorithm works, but it's definitely doing a lot more work. The smarter approach to do this is a sliding window. The key point in a sliding window is that, look, between two adjacent windows of data, there is in fact a significant overlap. So what does it mean, right? Basically, if I look at, let's say, subarray 1 and subarray 2, or say subarray 0 and subarray 1, you notice that these two items are in fact common. We are going to use this particular insight to create our smart algorithm, our efficient algorithm, and that will introduce us to this whole notion of fixed size sliding windows, which will take the complexity down from order of n square to order of n. That's for the next video, but I hope you found this interesting. Do look at our website www.ybyte.in, because at Ybyte we always learn algorithms and programming in a fun way. We always enjoy coding. Take care. Thank you so much. Bye bye.